Thank you. Thanks, Mike. Thank you. Okay. I sort of feel like rebutting the introduction, but I better resist that temptation. I want to thank Mike for the great introduction. Thank you. Thank you to the Falmouth Forum. It's a real honor for me to be here tonight. I come from that other institution up the road. I think it's really important for us to mix more. And so I'm thrilled to actually speak to the community and MBL, and hopefully we can do more of that. And as Mike described, I was assigned a topic by Mike. And so I'm going to stray beyond my expertise a little bit because I think it's really important. The question of sea level and the Antarctic ice sheets is really important. But I am not the expert. I was reminded of that by seeing at least one scientific colleague here in the audience who may know more than I do about sea level. And I think that's true anytime you speak in Woods Hole, that can happen. So just to start with a disclaimer. So this is a photograph taken from a helicopter in the Transantarctic Mountains. Most of the work that I have done is in the Transantarctic Mountains. And I thought I'd start with a beautiful picture because that was my other charge from Mike, was to show nice pictures. This is the Taylor Glacier that flows down into Taylor Valley, and we'll come back to that. Let's see if I can. Oh, before I start, I wanted to remember to thank people. There are so many people you can't possibly do it in a short thing like this, but there are some special people I want to acknowledge. The Noble Gas Lab in the Marine Chemistry and Geochemistry Department is really one of the world's best, and if anyone here is interested in getting a tour of that lab or NOSAMS, which measures carbon-14, please let me know. Colleagues who have done a lot of work in Antarctica with me, Robert Ackert, Ed Brook, Peter Clark, George Denton, who started me on Antarctic work in the 80s. My colleagues, my closest colleagues at NSF, Scott Borg and Alex Isern, and of course my family, who Mike already mentioned. Thank you to all of them. And there are a lot of people on here who are not acknowledged. It's really important to remember that. This photograph in the background is McMurdo Station again, from a helicopter. You can barely see some of the buildings here. It's actually very, very scenic from a distance. When you get close, I don't have any photographs, actually, when you get close, it looks kind of like a mining town. But I like it a lot. So the Transantarctic Mountains are here. This is the continent of Antarctica. Just to point out a few key things. The West Antarctic Ice Sheet is here. East Antarctic Ice Sheet is here. Ross Sea and the Ross Ice Shelf are here, McMurdo. And the New Zealand-based Scott base is right there. South Pole Station is right in the middle. So every direction is north. It's a little confusing. And what you notice is that the maps have the continents spun around depending on geographic interest. And the Antarctic Peninsula is here. The other American base, there are 3 American bases, permanent ones, Palmer, South Pole, and McMurdo. And Larsen Ice Shelf is right here. And we'll come back to that. That was the other part of my assignment. So this is a satellite image. It's really a continent of superlatives. It's the coldest, driest, windiest, highest, most remote continent. By highest, I mean highest in elevation on average. Obviously, Tibet is higher, but the average elevation is higher than any other continent. It has 90% of the world's ice, and it has 70% of the world's fresh water. So it really is an amazing place, but this is not all. It also has a unique history of exploration. And again, I want to point out these key features. These ice shelves, these are floating ice shelves. They're not underlain by rock. They're floating on the ocean. I'll come back to that in a minute. And to orient you, probably in an audience in Woods Hole, everybody knows this stuff, but I felt really that I had to do some basic introduction. To orient you, here is South America at the bottom, New Zealand is here, Australia is here, Africa is here. And this is one of the most ferocious oceans you can find on the planet. All of the famous voyages of exploration, Scott, Shackleton, and Amundsen, I believe, started in New Zealand. So these are it has no indigenous population, and it's the continent that is governed by the Antarctic Treaty, which I think is really an amazing document. It's set aside for research. There's no military activity. There's no mining or nuclear testing. And all territorial claims are set aside under the treaty. And the National Science Foundation represents the United States in the treaty organization. So there were 12 countries in 1961, and now there are 53 countries. And these are all the red dots are the permanent bases. The three American ones, South Pole, McMurdo, and Palmer. And I'm not going to talk about Palmer at all because I've not been there. And this is sort of a limited time thing, and I don't want to go over my time. So why we should all care about Antarctica? To me, this is a critical slide. It shows a transect. It essentially shows a profile through the two ice sheets across the Ross Ice Shelf. Remember, this is the Ross Ice Shelf here. It's floating ice. And the red dashed line shows this transect. Okay, so 0 on this diagram is sea level. And so what you see is the Ross Ice Shelf here is floating, and underneath it is seawater. And then these enormous ice sheets, the top of the West Antarctic Ice Sheet is about 2 kilometers. The top of the East Antarctic Ice Sheet is over 3, or on the order of 3 kilometers. And the key point the reason I like this slide so much is it shows the volume of ice that is actually resting below sea level. And that's the key thing. I'm going to come back to that a couple of times. Now, if you melted this whole thing, this whole ice sheet, sea level would go up by 5 meters. That's a lot. There would be water right here. If you melted this one, sea level would go up by 50 meters. So sea level would be up there. So it's an important thing, and I hope you don't think this is a doom and gloom talk, because this ice sheet, I'll say right now, is very, very stable, I think. There is some dispute in the scientific community, so no need to worry. One of the first people to point this out, particularly the stability of the West Antarctic Ice Sheet. Let me go back one. So remember, 0 is sea level, so the bed of the West Antarctic Ice Sheet is pretty much below that. Okay? First person to realize that or to publicize it was a guy named John Mercer, and he published this diagram in 1978, and the title of his paper was West Antarctic Ice Sheet and CO2 Greenhouse Effect, a Threat of Disaster. So it's still true today, but we know a lot more about the ice sheet. This is the map of the bedrock underneath the ice sheet, derived from radar altimetry from small airplanes. This is one of them. This is a Basler in McMurdo Station, and you'll notice it has radar on the wings. And with airplanes like this, there's now pretty much a really good bedrock map of the entire continent. And the red parts are sticking up. These are the Transantarctic Mountains. These are the little bits of West Antarctica that stick up. And then the blue parts are essentially below sea level. So just to drive home how important this is, I have to do this, I'm sorry. But I was told this was a general audience. You got to do this kind of thing. So this is the present coast of Falmouth. And this is what Falmouth would look like if you raise sea level by 3 feet, which is about 1 meter. Everybody here knows that. This is approximately the maximum projection for from the IPCC. I'll get back to what that is. That's the Intergovernmental Project for, I'll get to the acronym. I can't remember what it is. But it's a very important group that got together and made a best estimate. This is their this is their maximum, 3 feet. And you can see the coastlines have a little more blue. And Woods Hole is right here. It's got a little bit of blue, but probably we're okay here with 3 feet. 3 feet isn't too bad. The next one shows what 5 meters or 16 feet would do if the West Antarctic Ice Sheet melted. And here's the coastline, and here we're probably underwater here, or there's water lapping up against the stage or something like that. And Falmouth is a very different place. So I wanted to bring home that this is an important thing. And so your tax money is being well spent in the National Science Foundation. You could still make donations, as Mike asked you, but, and this is the worst case scenario. This is what New England would look like if all of the polar ice sheets melted. So this is Greenland, West Antarctica, East Antarctica. This is 220 feet. And you can see the little green bits are all that's left of Cape Cod up here in Bourne and Sandwich. So this is a big deal. I don't think there's, as I said earlier, I don't think there's any danger of this. I just think it's important to understand the magnitude of the ice sheets, the impact that they can have. So controls on sea level, and as I mentioned already, my disclaimer, I'm not an expert on sea level, and I'm not going to go into all the details, but I want everybody to know that loss of ice by glaciers is only one of the impacts, or one of the effects, or one of the things that can change sea level. One of the other important ones is warming of the ocean. If you warm the ocean, it actually expands, and you can have a higher sea level. You can also have changes in the water cycle between the ocean and land, which could raise sea level. And you can also have local effects, which are related to the history of a particular landmass. Like if there's been a glacier here, which there has been, you can have uplift. So I'm not going to talk about any of that stuff. I'm only going to talk about glaciers and ice sheets, but I wanted to make sure everybody knew it's not the only thing. It's not the only factor. So what are the controls on an ice sheet? The big controls are how much snow there is on top of the ice sheet, and then how much is being lost by calving. So it's a balance, essentially how much snow, how much loss. And there are a lot of things going on here. You have oceanography, atmospheric circulation, and a really important thing is what's happening at the bed of the ice sheet. And I'll come back to that point. So I thought what I would do is give you a kind of a personal tour. These are places that I've been, from the top of the Antarctic ice sheet down to the places where the glaciers are draining the ice sheet down to the Ross Ice Shelf. And that's what the next series of slides is. This is the polar plateau. It's really hard to capture this. It's flat and white. But I tried. I have a photograph. This is the polar plateau in northern Victoria Land. I had the pleasure of being there. It was really a fabulous day that I spent there. This is South Pole Station. It's flat and white. The only thing you can see is the new South Pole Station building and some of the debris, and there's a vehicle in the foreground. This gets a little more interesting. if you're like me and you love rocks. This is the Shackleton Glacier, which is in southern Victoria Land. And the glacier is flowing downhill from the polar plateau, which is back up there. And you can see the essentially the motion. And this is on the order of tens of meters per year, the motion. And this is the reason you can kind of get a sense of that motion is there's this debris band, which is called a medial moraine. This is the Swithin Bank medial moraine, named for a famous glaciologist. This is the Campbell Glacier, which is kind of a fuzzy picture, but it drains down into the Ross Sea. This is Mount Melbourne, which is a volcano. And then getting closer to McMurdo, this is Taylor Glacier. Remember, I pointed that out in the first slide. Taylor Glacier is flowing downhill into Taylor Valley here. And I'm going to come back to this slide because this is a glacial moraine that my group, has been involved in dating. A moraine is basically a debris band of rocks left behind, tells you where the glacier was at one point in the past. This is the other end of the Taylor Glacier, so this is the terminus. And these are smaller alpine glaciers. So hopefully you're already getting a sense there are different types of glaciers. You have outlet glaciers that drain the ice sheet. There are these small ones, these alpine or mountain glaciers that don't really have too much ice stored in them and they don't have much of an impact on sea level. And then you have the big things, the ice sheets and the marine ice sheets. So this is the Ross Ice Shelf near New Harbor. And you can see just by looking at this photograph, there's different age ice in the Ross Sea. These blocks are from previous years that have been frozen in, and this is younger ice. So it's complicated, even something simple like that. This is the Ross Ice Shelf near McMurdo Station. This is the Coast Guard icebreaker Polar Star, which is essentially making a path for the supply ship to McMurdo, which happens every February. And this is the Ross Ice Shelf. This is taken in November, and the this is the edge of the Ross Ice Shelf near Cape Royds. This is Mount Erebus. It's an active volcano. There's actually a lava lake in the top of the volcano. And this famous place is Cape Royds. This gives me the excuse to show you Shackleton's hut. This is the hut that was built by Ernest Shackleton in 1907 for his expeditions to try to reach, or his expedition to try to reach the South Pole. I don't have time to go into this, but if anyone wants to talk about it, I'm a fan just like you are. And then, of course, there are other huts, and Scott and Shackleton didn't get along too well, so they didn't share huts. Scott had his own hut, which he built for his famous expedition in 1910, and this is at Cape Evans. And it's a fabulous place for so many reasons. This is one of them. You get to see these kinds of things. And at Cape Royds, there are penguins. Got to have a penguin photograph in... these are Adelie penguins, and it's really another fabulous thing. These are emperor penguins. There aren't as many in the McMurdo region, but these are near Cape Crozier. So here are the three bases, and South Pole, McMurdo. Here's the Ross Ice Shelf again. I'm not going to talk about Palmer, as I said. And the way that a scientist gets to Antarctica is to write a proposal. It has to be fundable, and it has to be to do something important, otherwise it wouldn't be fundable. It also has to go through peer review, which many of us in this room know that it basically has to go to our competitors, and they have to like it, which is almost impossible. So here's McMurdo Station. This is the biggest base on the continent. The summer population is about 950 to 1,000. The winter population is about 150. And it's it's here. The buildings are here, and here's a panorama of the buildings. And this is, again, Mount Erebus that looms over the base, run by the National Science Foundation. This is the South Pole Station, which was recently rebuilt I think it was completed in 2011. It's an incredible facility. It has a very small population in the summer of about 155, and a winter population of about 50. And the last flight into the South Pole, or from the South Pole, is sometime around mid-February. The first flight in is sometime around October. So those 50 people who are wintering over, they don't see the outside world for that period between mid-February to, what did I say, mid-October. So, and here it is from a distance. The other thing I feel obligated to mention is how amazing the U.S. Antarctic program is. The logistics are just incredible. The ski-equipped airplanes, which are run by the New York Air National Guard, they're ski-equipped, you can see that here. It's so difficult to get fuel to the South Pole that in the mid-2000s, the program developed a system of transporting fuel on sleds. Essentially, they drag the fuel from McMurdo Station all the way to the South Pole. And that's a much more efficient way to do it. And here's a picture of one of those tractor trains. And it takes about 2 weeks. So somebody's going to drive for 2 weeks. It's about, this is about 900 miles, something like that. So this is what it looks like on the inside of one of these C-130s. Is not exactly the standard airline. There's only one guy in this view, who's actually working. This is Peter Clark, who is the one of the lead authors of the IPCC report on sea level. And I was there with him. He worked all the time. When you get to it feels great to get to the Ross Ice Shelf. Here's the plane. You can see the ski in the background. There's no other place quite like it. So what I've done in my career as a scientist is to fly to McMurdo and then pack up a camp. And this kind of summarizes the whole thing for me. These are two of my favorite people I've ever worked with, Robert Ackert and Becky Weed, and they're standing in front of this packed helicopter. You can kind of tell that we've put just about everything we could think of into the helicopter, and then you go out in the field and you camp right next to your work site and collect rocks, bring them back to the lab and make measurements. It's fantastic. This is a cartoon that my daughter Nellie did as a teenager, and I'm pretty sure it was inspired by my neuroses about packing, because I think this is me, and I've got a list, and it's kind of long, and there's a pile of stuff that I'm taking with me. So it says, tip number 1, this is a series that she did on traveling tips. The other ones are pretty good too, but some other night. Remember to bring everything you need, make a list. So I thought I'd show some pictures of camps. This is the Taylor Glacier. This is Beacon Valley. And these are Scott tents, which are named for Robert Falcon Scott. They are kind of, for many years, they've been the primary tent used in Antarctica because they're so good in high winds. This is another camp in Taylor Valley. This is an old photograph. You can tell this because it's a Navy helicopter. The Navy got out of logistics, Antarctic logistics, in the mid-1990s. So this is an old one. This is the Shackleton Glacier, another helicopters New Zealand. This is just a pretty picture. And one of the issues in showing these slides is there's not often, if you don't have a person or a tent in the slide, you can't get a sense of the scale because the views are so vast. And here are a few tents, and here are two people. And this is a lava flow that we dated using cosmogenic nuclides. I'll explain that in a minute. That is the same camp, actually. And there's a view of Mount Discovery in the background. This is another camp in Arena Valley, and the arrow here points to two tents. The scale is hard, and I can't even tell you what the scale is, probably something like 7 or 8 kilometers across here. And there's the same camp and the two Scott tents. And these two guys were my two Ph.D. students that were really, I would say, heroic in the scientific work that they did, and I owe a lot to them. Here's kind of, it turns out I didn't have very many pictures inside the tent. I don't know why that might be, but this is a picture taken by Chris Linder, and it's actually kind of cozy in there. There's a Coleman stove, and you can heat the tent up safely because there's a vent at the top. So how I got involved, I promise I'm not going to get too nerdy on this, but basically the thing that I have been most involved with as a scientist is dating rocks using what's called surface exposure dating, using cosmic ray produced nuclides inside the rock. And the way that works is the Earth always has cosmic radiation bombarding it. We have cosmic radiation hitting us right now. Don't worry, it's not too dangerous. It hits the major elements in the rock and makes these very rare isotopes, including helium-3, carbon-14. Those are two that we measure in Woods Hole. And this is an example of the reaction. So this is a photographic emulsion. So it's silver chloride, for those of you who remember what photographic emulsion was. Nobody uses film anymore. This is a silver atom being hit by a neutron, and it's breaking apart. And helium-3 and carbon-14, for that matter, are two of the fragments that come off. You can make just about anything from this reaction. It's just breaking apart an atom. And if you know the production rate, you can measure the age of a rock exposed on the surface and tell how long it's been exposed there. There are a lot of uncertainties and quid pro quos that I won't go into, but and we can all argue about them. So then what I've done is to bring samples back to the lab and make measurements. This is one of the mass spectrometers we use. Oops, sorry. A noble gas mass spectrometer. And this is an accelerator mass spectrometer, which is a special one for measuring carbon-14. And I mentioned this earlier. If anyone would like a tour, let me know. I'm going to skip the map because we had that already, kind of. I'm going to get to dating this moraine. So this is the Taylor II moraine at the edge of the Taylor Glacier. And you can see at some point the glacier, and the distance here is probably about 4 kilometers across. I have the next picture is what this thing looks like on the ground. This moraine is about 120,000 years old. And that's what it looks like on the ground. You would never see that in a terrain that wasn't a polar desert. This would be eroded and covered with vegetation. You might not even recognize it as a glacial deposit. But it's in Antarctica, it's perfectly preserved. And these are the two guys, Ed Brooke and Robert Ackert, who did a lot of this work. And we dated this moraine as 120,000 years old. So Ka is the abbreviation for thousands of years. So 120,000 years old. Well, so what? The interpretation is, and I'll get to this in a minute, the interpretation is that at 120,000 years ago, Antarctica was warmer and there was less ice cover in the winter, and there was warmer ocean in the summer, and there was more snowfall on the polar plateau, and the Taylor Glacier expanded. Okay. This is important for understanding how the ice sheets, how they operate. Here's another view of it. Here's that moraine, and you can see these bathtub rings go all the way up into the valley. And here's another one. This is another photograph of the bathtub rings farther out. This moraine is 2 million years old. Now I'm showing this because it says that Antarctica has been stable for on the order of, East Antarctica has been stable and operating in a similar fashion for the last couple of million years. So things aren't that unstable. I'm going to get to the unstable part in a minute. These are the bathtub rings as you go from the surface of the ice up, and you can see, and this is the Taylor II moraine here, this distinct one. And the camp was way up there that I showed earlier. So in order to put this in perspective, you have to understand the past. And one of the best ways to do that is with ice cores. So this is a temperature, and this is a record of temperature in blue and carbon dioxide in the ice as a function of time going back from 0, which is essentially today, to 400,000 years ago. And you'll notice the blue, which is temperature, goes warm, cold, warm, cold, warm, cold, warm, cold, warm. And those are the well-known climate cycles produced from variations in the Earth's orbit, which then change the solar insolation. These are orbital variations. And this has been known for years, but one of the best ways of understanding it is from ice cores. Now, I'm bringing it up here because our Taylor II glacier was advancing here during this warm period. And the other reason I'm bringing it up is that if we go to the present day, actually, let me go back one. So CO2 is doing a very similar thing. When things get warm, there's more CO2 in the ice or in the atmosphere. These are essentially bubbles in the ice. When things get cold, there's less CO2 in the atmosphere. Now, the reason for that is that essentially the ocean takes up CO2 as a function of temperature. And the warmer the ocean, the more CO2 it gives off. That's a little bit of an oversimplification, but it's approximately right. And these two things, temperature and CO2, are reacting to the forcing of solar insolation. If you compare what we have today, the present day CO2 in the atmosphere is about 400 parts per million. Here's the scale for CO2. The highest value in the last 400,000 years has been about 280. So we're way beyond that. And so the question is, what does that do to the atmosphere? Everybody here has heard of global warming and the greenhouse effect. This is, in a very simplified form, this is just a graphic illustration of that. So if we look back at the past, we know that sea level has also varied. This is another diagram showing today is 0, 35,000 years. This is the last glacial cycle. So we have a warm planet today. Sea level is 0. If you go back to the last glacial maximum, which is about 20,000 years ago, sea level was 130 meters lower than it is today. To me, that's amazing. When I first learned this as a graduate student, I couldn't believe it. Are you kidding me? Sea level was 130 meters, which is on the order of 360 feet, something like that. And the reason that it was so much lower during the last glacial maximum is there was all this ice taking up water in North America. This is the Laurentide Ice Sheet, which is Europe and Eurasia and North America. So this is North America here, and this is an approximate reconstruction of what that looked like. So if you look at the recovery from that glaciation, when things warmed up, you can see sea level went up between 10 and 15,000 years ago. It went up on the order of, 60 meters. And there are names, scientists love to give abbreviations. This is meltwater pulse 1A and meltwater pulse 1B. And there are debates on where that water came from. So I don't want to go into that, but. So what about today? What's happening in Antarctica? And that's where we come to the scary parts. This is a map of velocities. So you have to look at the color scale. This is, for those of you who can't read this, the red colors. So on the Ronny Ice Shelf and on the Ross Ice Shelf, these red colors are velocities on the order of 1 kilometer per year. That's how fast the ice is moving. And if you look on in the top of the East Antarctic Ice Sheet, the ice is moving very, very slowly. So what this is saying is essentially it's supported by the photograph I showed you of the glacier draining down into the ice shelf. These glaciers are draining the ice sheet. And the velocities are mainly controlled by what's happening at the bed. So the ice shelves are fast and the ice sheets are slow. So that's kind of, the same thing that I said earlier. This is where all the flow is, and the balance is between snow and ice accumulation at the top and how fast things are going out. So the key thing in the glacier is as I said, is what's happening at the bed. You have an ice sheet flowing out into the ocean onto an ice shelf that's floating, and seawater gets under there, and it can melt, and this thing can recede, and then what happens is the ice sheet flows faster, and it thins, and it drains the main ice. Where the glacier is frozen to the bed in two very important places, Pine Island Glacier and Thwaites Glacier. The grounding line is at a point where the bed slopes downward. So if seawater, and this was Mercer's fear when he wrote that paper in 1978, if you get water under here, you could essentially float the whole thing. And that's essentially why I pointed out that this is all below sea level. And those places, Pine Island Glacier and Thwaites Glacier are right there. And they are essentially protecting this West Antarctic ice sheet from invasion of seawater to the bed. That's the great fear. This is my assignment, the Larsen Ice Shelf. This is a time lapse of the Larsen. Let me go back and show you where that is. The Larsen Ice Shelf is right here on the Antarctic Peninsula, okay? This is actually in the news a lot because there are these beautiful images. It's actually not that important in terms of sea level because these are floating ice shelves. They don't contribute to sea level. What they do is protect, not here, but elsewhere on the continent, they protect the massive ice sheets. And so, of course, everything is relative to the state of Rhode Island. This is the state of Rhode Island. Gives you an idea of the size. Larsen A collapsed in 1995. And this time lapse goes from 1986 to 2002. I think this is what you were referring to, Mike. There was another one, Larsen C collapsed in 2017. I don't have a photograph of this, but this is, I think, an amazing documentation of what's happened to the Larsen Ice Shelf. And it's important to remember that the reason this is melting or disappearing, there are two things. There's oceanographic conditions, is seawater circulating down below, and also warming from above. It's both things. Now we're getting to one of the key things that's been fairly recent is the study of the grounding line retreat as a function of time. This is from a very recent paper. This paper was published last week by Hannes Conrad and colleagues. I think they're based in Britain. And they used a satellite called Cryosat-2 to map the grounding line of the glaciers. And if the grounding line is moving inward, it has a blue color. And if it's moving really fast, it has a purple color. Here's the scale up here on top. The zero migration, in other words, things aren't happening at all, is white. So East Antarctica, there isn't very much happening. The grounding lines are not moving that much. But in West Antarctica, where we have all these blue and purple colors, particularly here, Pine Island Glacier and Thwaites, the grounding line has been moving inward at a rate of 200 to 300 meters per year, which is really fast. There is some good news in this, in that the Pine Island Glacier has slowed a little bit from the previous study, which was 1992 to 2011. So, you know, it's not all bleak, but there is a real reason to worry about the collapse of the West Antarctic Ice Sheet. So this is another perhaps more clear illustration of this mechanism, where you get warm, deep water underneath the ice shelf, the grounding line retreats, and eventually you get to a point where seawater can invade the whole thing. This is the reason for concern about the stability of the West Antarctic Ice Sheet. So what about the future of sea level? This is the 5th assessment report of the United Nations Intergovernmental Panel on Climate Change. I got that wrong. IPCC. It was written in 2013 and it was published in 2014. And this is a projection starting in the year 2010, going out to 2100. And these are projections based on different CO2 levels in the atmosphere. And I think it's fair to say that they're highly uncertain. That's why they're big error bars. So remember, we're at 400 parts per million. This lowest one, so that would be this lowest bound, has 421 parts per million CO2 in the atmosphere. The upper one is 936 ppm. That would be kind of what's referred to in this business as business as usual. In other words, we just don't worry about burning fossil fuel. We continue to put CO2 in the atmosphere. The Earth warms. And this projection is based on global climate models and ice sheet models. And it has sea level going up by about a meter by 2100. So this is where I got the upper bound of 3 feet earlier in the talk. I think this is actually, unfortunately, I think this is conservative. I think it's because it did not consider, this model did not consider instability of the West Antarctic Ice Sheet. So this is a model projection. I think everyone is wise to be skeptical of a model projection because it involves a lot of uncertainties. These are measurements from satellite-based altimetry. This is also very recent. This is a 2018 paper, and it shows the global mean sea level in millimeters. So we go from, and the scale on the bottom is year. So this is 1995, and the most recent observation was 2017. And you can see it's pretty well measured using satellite altimetry. Extrapolating this out to 2100 gives you about 65 centimeters or something like two and a half feet, something like that, by 2100. That's very close to the IPCC report. So might be okay. The question is, how stable is the West Antarctic Ice Sheet? We really don't know the answer to that. And I think that is where, I think I'm actually ahead of time. Take-home messages. This is a typical nerdy thing to do for scientists. You've got to leave a take-home message. I got to do that. Antarctic glaciers and ice sheets are important. Hopefully I convince you of that. I also think they're fabulous. They're easy to appreciate them just from a natural point of view. Sea level rise is real. It's not something that we can ignore. I personally think it would be a very good idea to reduce carbon emissions. I'm not running for office. We can expect at least 70 centimeters. This is based on the projection and the actual measurement of about 70 centimeters by 2100. This is actually a lot, even if the West Antarctic Ice Sheet is stable and doesn't melt. This is still a lot, and it's something that we need to plan for. And as I said, this is probably a minimum due to the evidence that the West Antarctic Ice Sheet is becoming unstable. So that's all I have. I'd be happy to entertain questions. Thank you very much. This is John Stegeman. Are you going to ask a question?
No, I'm good.
Oh, I thought for sure you were going to give me a hard time.
Well, I will ask, but not right now.
Mark, I think it's worth pointing out that sea level rise doesn't stop in 2100, and it just keeps going and keeps getting worse.
That's a really good point. Thank you.
For centuries, because the lifetime of CO2 in the atmosphere is millennia.
Excellent point. The guy that I was mentioning, Peter Clark, who was a co-author on the IPCC report, has a really nice paper that actually, I think he extrapolates out 10,000 years. So I just didn't feel like I could include that, but it's an excellent point. Yeah.
There's a question here, Mark. Question over there first.
Hi, a comment and a question. I deal with the Arctic, not the Antarctic, but I do know that two things. One, the IPCC calculations did not include the advent of the methane that's being emitted from the melting permafrost in the Arctic. So in their new report, that number will probably doubled, if not tripled. So heads up, Falmouth. But my question for you is...
Good comment.
The Arctic is increasing in its temperature at a far greater rate than the rest of the Earth. It's at about 6 degrees centigrade already right now. And I'm wondering what kinds of observations have been made in the Antarctic regarding surface temperature. You mentioned something about increasing temperatures, and I'm wondering if it's almost as extreme or as extreme as the Arctic, and would that accelerate melting down there?
You know, I have not personally been involved in temperature measurements other than to say, wow, that's cold. It's pretty clear that the Arctic has been warming faster than Antarctica. I think that's your main point. And because of the isolation of Antarctica, I meant to point that out when I showed that introductory slide showing the southern oceans surrounding the continent. It's way colder and way better insulated from warming than the Arctic. So in reality, melting in the Greenland ice sheet is also a really serious question. So it's an excellent point.
Okay, thanks. And
if I give this talk again, I will mention that.
Thanks. Just one other point of doom for the audience is that Admiral Zukunft, who's the Commandant of the Coast Guard, is using 2 meters as his basis point for planning for new Coast Guard infrastructure for the end of the century.
2 meters for 2100,
Yeah.
which is, it's actually, yeah, it's double the IPCC. Yeah, yeah.
Question here.
Yes, could you comment?
Thank you very much.
Could you comment on the regional variations in sea level rise that might be occurring?
You know, I can't really because I'm not an expert in that. I do know that North America, parts of North America are going up because of essentially glacial isostatic rebound. I can't tell you the details, I'm sorry. I should remember them, but I can't. Maybe there's somebody in the audience who knows. Ray, do you know?
There's also changes in the ocean circulation that will affect sea level rise.
Right.
Sea level rise is faster in the northeast because the Gulf Stream's been slowing down. And so sea level at Bermuda.
Repeat that into the microphone. We have, this is Ray Schmidt, who's a physical oceanographer at Woods Hole Oceanographic Institution.
Yeah, there are a number of things that affect the regional change in sea level. Mark mentioned isostatic rebound because the continents are still adjusting to the loss of ice when the glaciers retreated. There's also an interesting effect. When you lose a lot of ice, say from Greenland, it reduces gravity, the gravity of all that mass. And so sea level around Greenland will actually fall a little bit.
Because you're losing mass.
Because you're losing the gravity due to the mass of the ice on the shelf. And then the effect that I was trying to mention was changes in ocean circulation. Right now, the Gulf Stream is maintained by about a 1 meter change in sea level from Bermuda to the East Coast. And as the Gulf Stream weakens, partly because of all this fresh water being put in at high latitudes, that difference will drop. And so sea level on the East Coast, say from Virginia to Nova Scotia, has been rising faster than the average sea level.
That was a great answer. Thanks, Ray.
So if I could ask, Ray mentioned rebound. Could you explain that for the audience, please?
Okay, well, I'll do my best. Rebound is probably less important than what Ray was just talking about in terms of temperature and ocean circulation. But if you load a continent with an ice sheet that's kilometers thick, it will sink, it will get depressed by the sheer mass of the ice. And then when you remove the ice, it takes thousands of years for it to essentially rebound. So that's a local effect. And I thought that's what he meant, but Ray's answer was good.
So we're still rebounding here
Yes.
from the glaciation.
Yep. I can't tell you by what rate, but we are.
If the West Antarctic ice sheet did collapse, what would be the time frame of that? I mean, does it suddenly go boom, or is it very slow? How much time would there be to adjust to it?
You know, there's really no way to know that, but that's one of the reasons that there's so much interest in this sea level curve. You know, one view of understanding the Earth is that the past is, you know, some indication of the future, that kind of thing. And you'll notice this curve, there's a very steep part, that's meltwater pulse 1A. Your question is one reason to study that. How fast could the West Antarctic ice sheet collapse? We don't know. But if we could figure out where it was and understand the mechanisms by which it collapsed and whether it was analogous to the West Antarctic ice sheet, maybe we could put constraints on it. So I don't know the answer, but this is something like 20 meters of sea level in, I think it's less than 1,000 years. So if you're worried about your, waterfront property you're probably okay. I'm trying to be reassuring here.
For now.
Yeah. You could donate money to the scientists. It's tax deductible.
One of your early slides showed 53 nations that were working at various research points through Antarctica. Are they collaborating on this research, or are they all doing their own thing?
There's a lot of collaboration, but they all obey the Antarctic Treaty, which means if somebody wants to build a new base, they have to go before the Antarctic Treaty, and everybody has to agree to it. So and there's a lot of collaboration. So when I had the pleasure of working at the National Science Foundation, there were often requests for collaboration between the United States and other countries. And there was often a quid pro quo arrangement where somebody would say, we have this research project, we want to use your airfield. Is that okay? That kind of thing. So yes, it happens all the time. And I would say the international collaboration for me, is a highlight of the Antarctic program, because I think there's more collaboration there than in other domains because of the kind of shared difficult conditions and logistics. It's really expensive. The United States spends something like $300 million a year to support those 3 bases, plus the science. But in fact, the science is a little bit less than the logistics.
To continue with that question, you have 53 entities worldwide who are sharing basically facilities and access. Do they actually get together and do research together? Do they collaborate in that way?
Well, it's ad hoc. It's up to individual investigators to get together and collaborate. But there are collaborations, yes, and there are also shared. I mean, it's kind of a question of logistics. Scott Base and McMurdo Station are basically walking distance. They collaborate a lot because it's pretty easy. Anyone who wants to use the South Pole has to collaborate with the United States because the United States has the only base. There is actually a tourist company that runs trips to the South Pole. What's the name of the company? Does anyone know? AIL. Anyway, you can buy a ticket to the South Pole. I'm sorry, that doesn't relate to your question. But yes, there's collaboration, but it's kind of ad hoc. Each country has the same constraints that we do, which is limited resources. Each country has their own kind of research infrastructure, proposal structure, that kind of thing.
Wouldn't the whole thing work better if they got together and said, okay, let's solve your rock problem together? 4 countries out there solving the rock problem. There isn't a mechanism or an agreement to try to do that kind of work?
Well, there is, but I mean, it's cumbersome in the same way that, collaborating with somebody in some other country. And I think, well, in terms of the United States program, there's a favorability to projects that involve international collaboration. It says that right in the solicitation for proposals, that international collaboration is a plus. And I meant to mention this actually, this is a good answer to your question. The United States and Britain, United Kingdom, have the planning stages of a collaboration to study the Thwaites Glacier. So there are formal programs, but those are rare. But it does happen.
So why don't we just say maybe one more question? And before we take that last question, Mark, I had a little senior moment when I was introducing you and I forgot to mention something. And that is there's going to be a Science Before Supper program on April 12th at 5 o'clock at the library. It's going to be done by Kristen Gribble. And the subject is going to be understanding aging, which I think we're all kind of interested in. So I just wanted to let you, make you aware of that.
Are you going to go, Mike?
I said, Falmouth Library. Pardon me? What was that? Okay, you one more question? Okay. It's at the Falmouth Library. I guess I said I said something else. The Falmouth Library.
We have another question right here. This is Carl Bowen. Carl.
Aside from the volcanoes, most of the strata seem to be horizontal, like the Rocky Mountain Plateau. Are they folded strata?
In the photographs that I showed?
Yes.
So a great question. The photographs are of the Transantarctic Mountains, and you have essentially a geologic sequence that's uplifted on the West Antarctic Rift system. So
I didn't see folded mountains.
No, it's essentially East Antarctica is on older crust and West Antarctica is on younger crust. It's one of the reasons why there's this difference in elevation of the bed of the two glaciers. It has to do with the bedrock geology. So the white band that you saw in some of those photographs is the Beacon sandstone, which is Devonian, which is something like 400 million years old. It's not quite analogous to the Rocky Mountains, but you know, I should have said something about the geology. So, thank you.
If I understand one of your early slides correctly, you say that Antarctica has 70% of the total fresh water in the world.
I did say that in the slide.
I assume that's because
it's up to you to tell me whether it's right or not. Ray says it's wrong. What should the number be? 40% says Ray in the front.
40% is more believable.
I don't know where I got that number, but thank you. I'd much rather be right. Well, thank you very much. I appreciate it.